So welcome once again in the class of water resource engineering. Again we are continuing the groundwater hydrology. Today we are going to see few things about the permeability. I am Mr. S. Sogule, Assistant Professor, Civil Engineering Department. So to begin with the permeability of soil. Permeability is the measure of the soil ability to permit the water to flow through its pores or voids. You have learned this thing in the soil mechanics or the geotechnical engineering. So the knowledge of the permeability properties of the soil is necessary to first is for the estimating the quantity of underground seepage, and second solving problem involving the pumping seepage water from the construction excavation. So for these things we need the knowledge of permeability. So the factors affecting permeability of soil are grain size. The smaller grain size, the smaller the voids, thus the lower the permeability. In the void ratio, increase the porosity leads to an increase in the permeability. Then composition, the influence of soil composition on permeability is generally insignificant in case of gravel, sand and silts unless mica and organic matter are present. Then the soil structure, fine grained soils with flocculated structure have a higher coefficient of permeability than those with dispersed structure. The degree of saturation, higher degree of saturation, higher the permeability because it soaks less water. Then the presence of entrapped air and other foreign material reduces the permeability of soil. The organic foreign material may choke flow channels, thus decreasing the permeability. Then coefficient of permeability of soil. Oh, so what are the measurement of the coefficient of permeability of soil? First, there are some laboratory tests that is using Darcy's law. You might have done some laboratory test in the that soil mechanics, that is falling at the method, constant head method. Those are these things. The constant head permeability test suitable for the coarse grained soils, falling or variable head permeability test suitable for the fine grained soils. Then the field test, that is pumping out test and pumping in tests. And indirect methods are computation from the particle size and computation from the consolidation test. So these are the methods of measurement of coefficient of permeability of the soil. Then the Darcy's law. So the Darcy's law is an equation that describes the flow of fluid through the porous medium. The law is formulated by Henry Darcy in 1856 based on the results of experiments on the flow of water through the beds of the sand. For the laminar flow through the saturated soil mass, the discharge per unit time is proportional to the hydraulic gradient. So this is the Darcy's law. What? For laminar flow through the saturated soil mass, the discharge per unit time is proportional to the hydraulic gradient. So what are the assumptions made defining Darcy's law? First is the flow is laminar, that is flow follows a definite path and does not cross the path of other verticals. Then second thing is water and soil are incompressible. That is continuity equation is assumed to be valid. Third is what the soil is saturated, and the last one is the flow is steady state. That is flow conditions do not change with the time. Now here you can see Darcy's law apparatus. So this is the Q, that is discharge, which depends upon this coefficient of permeability, and A is the area, and this H by L, that is hydraulic gradient. So this is head loss, that is HL, and this is the length that to which the water flows. So this is the Darcy's law apparatus. Then typical values of coefficient of permeability for various soils are as follows. For the coarse, this is the range 10 to 10 raised to 3. Fine gravel, coarse medium, that is 10 to minus 2 to 10. Then fine sand and loose silt 10 to minus 4 to 10 to minus 2. Then dense silt, clayey silt 10 to minus 5 to 10 to minus 4. And for silty clay 10 to minus 8 to 10 to 5. So these are the coefficient of permeability for the various ranges of the soil or soil types. Then the pumping out tests. Now the Lipid theory. The coefficient of permeability of the permeable layer can be determined by pumping from the well at a constant rate and observing a steady state water level in nearby observation wells. The steady state is established when the water levels in the test well and the observation well become constant. When the water is pumped out from the well, the aquifer gets depleted from the water and the water table is lowered, resulting in the circular depression in a phreatic surface. This is referred as the drawdown curve or a cone of depression. The analysis of the flow downwards such a well was given by the Dupuit in 1863. So, what are the assumptions for this theory? The aquifer is homogeneous, then Darcy's law is valid, the flow is horizontal, the well penetrates the entire thickness of the aquifer, the natural groundwater regime remains constant with the time, and Dupuit theory is valid, that is I equals to dz by dr. At dz by dr we are going to see in the coming part. Here you can see we are discharging the water from the well with the pump or something, and initial water level is somewhere like this, and because of this discharge or pumping the water, what happen, this particular water table is goes down. So this distance is we are taking as r and this height is z side. So this is the piezometric surface under the pumping, and uh, this is the pumping out test look like. So here we have the two expressions for the two cases are there, that is first is for unconfined aquifer and second is for the confined aquifer. So first case is for unconfined aquifer, the pumping out test. So let r and z be the radial distances, where you can see these are the r and z distances. So as I have told you earlier, these are the observation wells. You can see over here initial water level is something like this, original water table, and we are pumping the water from this well. So obviously what will happen, this water goes or water table goes down up to this is drawdown curve or a phreatic line. So r and z with the distance and the height above the impervious boundary at any point on the drawdown curve as shown in this figure. At steady state, the rate of discharge due to pumping can be expressed as q equals to k into I into a. K is the coefficient of permeability, I is the hydraulic gradient at any point, as we have seen over here in this Dupuit theory. This is the hydraulic gradient and A is the area. So the hydraulic gradient at any point by Dupuit theory is I equals to dz by dr. This is the Dupuit theory. So this is I equals to dz by dr. So by putting all these values, the q is equals to k into dz by dr into 2 pi r into z. That area is 2 pi r, that is the um, periphery of that well, and z is the height, so that is the surface area. So again this dr we are taking over here, dr by r, and q is we are taking from this side to here, that is 2 pi k divided by q into z dz. Now we are integrating both sides, that is from limit r1 to r2, and this is for the z1 to z2. So what we'll get here is k equals to 2.303 q pi into z2 square minus z1 square into bracket log to the base 10 r2 divided by r1. You can note here that z1 is equals to h minus t1. You can see this is the overall height h minus d1, and z2 is h minus d2. So what we'll get is k equals to 2.303 q pi d1 minus d2 into bracket complete into 2h minus d1 minus d2 to the log 10 into r2 divided by r1. So the values of this r1, r2, z1, z2 and q are known because we are measuring or observing this thing from these wells. So obviously we know the h and we know that this d1, d2, all the values we know. The coefficient of permeability can be calculated by using this relationship because these values are known. Even d is also known and even z is also known. Now for the confined aquifer. So you can observe here we have the impervious stratum over here and aquifer is located over here. In earlier case we have the full range because it is the unconfined aquifer. So again r and z will be the radial distance and the height above the impervious boundary at any point on the drawdown curve as shown in this figure. At steady state, rate of discharge due to pumping can be expressed again Q equals to KIA. So here we are putting Q equals to K into I is dz by dr as we have seen earlier, and here the area is 2 pi r into h. Now this is the h because this is the confined aquifer because water is coming from only this much area. This is the water coming from this area. In earlier case, the water is coming from the entire area. Here you can see. Hmm? So H is the depth of the confined aquifer. Now the KdZ equals to Q divided by 2 pi H into dr by R. So K and dz we are taking over here and all the terms we are rearranging. So again by integrating both sides by these limits z1 and z2 and r1 and r2, what we'll get is k into this z into q divided by 2 pi h log to the base e into r, that is r1 to r2. So k equals to 2.303 q divided by 2 pi h z2 minus z1 log 10 r2 to r1. Then again by simplifying k equals to q divided by 2.7283 into h into z2 minus z2 into log 10 to r2 by r1. Again note this z1 is h minus d1 and z2 is h minus d2. So finally we will get k equals to q divided by 2.7283 into h into d1 minus d2 and log 10 to the base r2 to the r. So here you have to make the correction. If the values of R1, R2, Z1, Z2, Q are known from the field measurements, we can calculate the coefficient of permeability by using these equations. So by using this equation, or we can use this equation for the calculation of K. So this is all for this lecture. The references are again this website and the book. Thank you.